Here is the official chain rule. Let f and g be differentiable functions. Then capital F of x, which is f composed with g of x, is differentiable function and its derivative is given by f prime of g of x times g prime of x. When we are going to use the Leibniz notation, we are getting the following chain rule. Let f and g be differentiable function. Let u be g of x. Then I will call y f of g of x, but when you substitute u for gx, you get actually that y is f of u. This function, y equals f of u, is differentiable function, and dy dx equals dy du times du dx. Please notice that in the Leibniz notation, you can cancel the du's and you will get the dy dx indeed equals dy du times du dx. This is like substituting for the inside function the variable u. And here is the useful chain rule, the one that you will use to really differentiate. D dx of f of g of x equals what? First of all, we will do u substitution for g of x. So the inner function in the f is going to be u. U equals g of x. This is a non-composite function of x. But now let's observe what happened to f of u. Y, which equals now f of u, is a non-composite function of u. And the useful chain rule says that if you do that, then the derivative is just the product of the two derivatives of the non-composite functions. First of all, the derivative of y has to be dy du, which means it is the derivative of y with respect to u, because as you can see, y equals f of u, which is a non-composite function of the variable u. And then, what about the derivative of u? It has to be du dx, because u is a function of the variable x. And again, you can recognize that, and you see that indeed we get dy dx, which is just the derivative of f of u. Dy dx of f of g of x, in this setting, we are going to use the same substitution, it's just we are going to write it differently. We are going to take the derivative of the outer function f, and because this is now a function of the u after the substitution, it's f prime of u times the derivative of the inner function, which is u prime. Example: d dx of sine of x to the power of 2. If you observe the parentheses, you see easily that the inner function is x to the power of 2 and the outer function is sine. This function was made by taking the sine and instead of just sine of x, writing x to the power of 2 instead of x. So this is a composition of two functions when the inner function is x to the power of 2 and the outer function is the sine function. Now we can even check further. If we will replace the inner function by a u, then sine u is a non-composite function of the u. And if so, we can conclude that u is x to the power of 2 and it's a non-composite function of x. And the outer function, the f of u, is sine of u, because this is exactly what I see there after I covered x to the power of 2. And this is a non-composite function of the u. So in this chain rule, we are going to get two terms. We have to differentiate these two functions. The first function, f of u, the outer function, is the derivative of sine of u. It's clear that it is d du, because the outer function now, after the substitution, is a function of the u. It is sine of u. Then we have the other term, which is the derivative of the inner function. The inner function is a function of x, so it's a clear d dx of x to the power of 2. Now we just have to differentiate each one of these functions. Another way to view it is just the derivative of the first one times the derivative of the second one. But you have to be careful if you write like this. The derivative of the first one has to be a function of the u because the function is function of u. And the second one, it's a clear cut, the derivative of x to the power of 2. We get from the yellow cosine of u and from the second one 2x. It's customary to write the 2x before, but it really doesn't matter right now. I want to focus on the chain rule. So as you can see, the only thing that we had to do now in the last step is really just to replace u by x to the power of 2. Another example. d dx of e to the power of 3x to the 5 plus 1. This is certainly the u. And we get that the u is 3x to the power of 5 plus 1. This is a non-composite function of x. And the outer function is clearly e to the u. This is another non-composite function, but now of u. And for the chain rule, we have to differentiate these two functions. Again, we will differentiate the f with respect to u because it is a function of the variable u. And we will differentiate the second one with respect to x because this is a function of the variable x. Another way is just to use this notation, but then please pay attention to the variables of each one of the two functions. The yellow function is a function of u and the second one is a function of x. And we get e to the u times 15x to the power of 4. Now replace the u by the u, which is 3x to the 5 plus 1. And we get this instead of e to the u. And this just copy. This is the answer. Example. d dx of 2x to the power of 2 minus 3x plus 5 to the power of 9. The inner function is pretty clear here because it has parentheses around that, and the outer function is a power of 9. The inner function is going to be the u, and it is 2x to the power of 2 minus 3x plus 5. We can check again. We cover that by u, and we see not only that this is the u, but we also discover that way what is f of u, and f of u is u to the 9. The product of the derivatives, and we get this from the first, this from the second. And the only thing left to do is to replace u by the function written as a function of x. And we get that. Example, d dx of e to the power of e to the x. Now you can recognize that this is e to the power of a function. It means that this function has to be the u. U is then e to the x. Now you can check that, but also by doing this, you discover what is f of u. F of u is e to the u. Just differentiate both of them. So as you can see, e to the u should be differentiated with respect to u because e to the u is a function of the variable u. And the second one, you have to differentiate with respect to x because it is a function of x. Now we will replace u by the u, which is e to the x. And we get that. Example, d dx of sine x. You can see that the inner function is sine of x. A big clue here is the parentheses. So u is sine of x, and f of u is sine of u. We differentiate that, and we differentiate that. And we get cosine of u times cosine of x. Now let's replace the u by sine of x. We will get cosine of sine x times cosine x. Please be careful here. Sine of sine x is not a product, it is the sine of x. Example, d dx of 5 times e to the 5x. There is here first of all a constant rule with a 5, and then a chain rule with e to the 5x. So it is 5, first of all, from the constant rule, and then u is 5x, and the big function f of u is e to the u. And we get 25 times e to the 5x. Example, d dx of ln of 5x plus 1. This is certainly the u, and the outer function is ln of u. So here's the product of the derivatives. It's d du of ln of u and d dx of 5x plus 1. The first one is 1 over u, and the second one is 5. Let's replace the u by the function. We get that, and then times 5. And we get 5 over 5x plus 1. In general, let's apply the chain rule for ln of fx. The inner function du is f of x, and the outer function is ln of u. So the derivative is 1 over u times f prime of x, or if you want, du dx. 1 over u is 1 over f of x, and du dx is f prime of x. If you noticed, we get the following. If this is a fraction line, then the function fx is written here, and on top, we just have to differentiate the function that is in the denominator. And we can conclude something very useful. That d dx of ln of f of x is the quotient of f prime x over f of x. For example, what is d dx of ln of sine x plus x? So the easiest way to do it is just to write a fraction line. In the denominator, I'm just copying the function, and in the numerator, I'm just differentiating, which means it's a cosine x plus 1. Example, d dx of ln of cosine x. It's enough now to recognize that f of x is cosine x, and its derivative is negative sine x. So if this is the fraction line, here I'm going to write the function, and here I'm going to write its derivative. And look, in this case, we get negative of tangent x.